So now the aim of a statistical experimental design or optimum experimental design is to obtain parameter estimates with the smallest possible uncertainty. And now, if we talk about the covariance matrix, there is not a unique way to define what does small mean. And accordingly, there are a number of criteria that have been proposed. For instance, you can try and construct an A-optimal design which minimizes the trace of this matrix here. So when I say minimize the trace, what does it mean? It means that at the outset, somebody defines the range in which you can perform measurements. So let's say you assume that you have a linear relation that you want to model, and let's assume that you can direct your measurements in let's say we have two explanatory features. Let's say one feature is the laser power, and the other one is transdimensional fudge factor. I'm making up something, okay? So let's say you have control over these two dimensions. You assume that you have a linear model here. You would like to fit a plane. And the question is, where should you put your measurement points? So intuitively, where do you think, if you want to fit a linear model, where would you put your measurements? Spread out? On a grid, you said, or just spread out?
Not necessarily a grid, I guess, but spread far enough in each dimension to constrain the plane.
Okay. So would you actually, I'm luring you into the wrong answer now, but never mind. So would you really take a grid, or how would you distribute your points? So let's say I'm giving you, a budget of 16 points, for example. Where would you put your 16 points?
I guess you probably want repeated measurements nearby to reduce error. So
if you're sure that it's actually linear, you can just take points at the bottom and at the top.
Yeah. Mm-hmm. Yes, I love this answer. This is the correct answer. Okay, so the answer was, let's say we have a budget of 16 points, then this algorithm here would tell you, okay, let's get 1, 2, 3, 4 measurements here, and we have 12 to go. Okay, so let's put another 4 here, and another 4, and another 4. So you would perform these repeated measurements, and this is the optimum experimental design that you can get. So this is what is going to give you the smallest uncertainty in your parameters, provided that you can be really sure that the linear relation holds. But if you have no point in the center, you're never going to find out if your relation actually holds or not. No? Oh, I just said, I just randomly said 16. And Yeah, but I think, no, I'm sure that, so the question was, I'm reproducing this plot. If you're given a budget of 4 points, why not put 1, 2, 3, and then put the fourth one here again? And the answer is that uh, compare this matrix here, XX transpose. So I haven't spoken yet about Gaussianity, but if I did, I could now draw ellipses, and to fit these points here, I would, get an ellipse that looks something like that. Whereas if I put my points 1, 2, 3, 4, I get an ellipse which has more volume, and hence it will have a smaller inverse, as by some measure, and in that sense will give me smaller errors on my parameter estimates.
Will also reduce the error on the lower right corner if you repeat the measurement twice.
But I don't want to minimize the error in any corner. I want to minimize the error on my parameter estimates, and the parameters hold globally. So under the linear model, you want to distribute your points such as to get the maximum spread in some sense. And the optimal design minimizes the trace of this inverse scatter matrix here. Then D optimal design maximizes the determinant of XX transpose, and E optimal design maximizes the minimum eigenvalue of XX transpose. So if you assume Gaussianity, then you can draw ellipses, and you can interpret all of this in terms of the ellipses. So this one, the determinant is related to the volume, and you say that you want to get the largest volume ellipses here, or in this case, you want to make the shortest axis of the ellipses as long as possible, and so on. Yeah? So these are different measures that all try to achieve similar things. But as you rightly said, all of these things only make sense if the model can, if the linear model can safely be assumed to be true. Because even if you are, according to these criteria, even if you're willing to invest 100 measurements, you would put your measurements only at the corners and you would never look inside. Now it changes a little bit as you go away from linear models. If you take quadratic surfaces or cubic surfaces, then you start to see points more of the inside of your domain. However, even then they're starting to move inside your optimal measurements, but they're still concentrated on the outside. And then in contrast, and this is now just as a side comment, there is another line of work about space filling experimental designs. Where you make no such strong assumption that a linear model holds. And this is related to the packing of spheres and such things. Okay, now this is a one-page summary of a vast research arena. So you have entire journals devoted to this topic and thick textbooks. But if you remember that, you know what a large part of the literature is about. And of course, there's much, much more in there, but this is the basic idea. Yes?
What exactly are the limits of the dimensions in our toy example here? Just
Okay. What are the limits of the dimensions? So if I did not impose any limits, then my criteria would tell me, please move this measurement point to plus infinity and that one to minus infinity. And usually your experiments cannot realize that. So you yes, yeah, what your apparatus can do, or where the experiment starts to get too expensive, or something like that. Okay. So we've talked about the distribution of, or the spread of your parameter estimates. You can actually also compute the spread of your predictions in a very similar fashion. So I'm replacing my estimates by the observed values multiplied with the hat matrix. And the observed values are a random variable in our model because they depend on this random noise term. So this is y, and I'm multiplying this with the hat matrix. And then using the same kind of consideration as before, you come up with the following. And this is sometimes visualized by bands. So you can, for instance, say that this is my prediction y hat. And then I have an uncertainty band here. And in a similar fashion, you can compute the residuals, or the distribution of the residuals. And interestingly, the residuals are not uncorrelated. So your fitting a model leads to correlation of the residuals. Okay, now a word about whether parameters are significantly different from 0 or not. For example, you can look at the following: the null hypothesis that the parameter associated with the ith variable is in fact 0, or the alternative hypothesis that it is different from 0. To perform this hypothesis test, you need a test statistic, and the statistic that's being used is the parameter estimate that you found divided by the variance of that parameter estimate, the standard deviation of that parameter estimate. And if you now make additional assumptions, so if you assume that your error term was Gaussian, then if you obtain beta by a series of linear operations, then you find that beta is also Gaussian. So this will have a normal distribution. And then the variance here will have a chi-square distribution. And overall, you find that this test statistic T follows a student T distribution. And I'm not showing the math here. Student T distribution with n minus p minus 1 degrees of freedom. So as a reminder, student T distribution, if you let the degrees of freedom go to infinity, it becomes more and more like a Gaussian. But if you have small degrees of freedom, so in our case here, if you have, for example, few points in high dimensional space, then you get a very heavy tail distribution. Or in other words, if you fit few points in multiple dimensions, then there is a good chance that your non-zero parameter estimate is indeed just a manifestation of noise, and that really this independent variable does not contribute to your response. Yes. Okay. So if this epsilon is normally distributed, so we always said that its expectation must be 0. But if it's normally distributed, if I say that it has a Gaussian distribution, then beta well, I'm writing out y, which was beta 0 transpose x plus epsilon. So, sorry, this is not readable. So we just said that this thing here is normally distributed. That term here is just deterministic. And if I now multiply normal distribution here with some kind of linear term, so this is a linear transformation, it remains a normal distribution. So then beta hat is also normally distributed. So this term here would be the mean, and the covariance matrix you've seen before would be sigma squared times xx transpose to the -1. Okay, and this only holds if I assume that my random errors were Gaussian also. Now, this test here, or a result of this test is the following. Let's say that I found beta hat to be this, and if my covariance structure looks like that, so if I just look at the numbers, then beta 2 is larger than beta 1. So it looks like beta 2 is the more significant coefficient. But according to this test statistic here, because I'm normalizing by the standard deviation of these distributions, in this case here, beta 1 would actually be more significant than beta 2. Because you see, if I interpret these lines here, and I've again used here a Gaussian distribution, if I interpret these lines as distorted distance isocontours, then this axis here is closer to that point than that axis. And this is what, so this distorting of the isocontour lines, of the Euclidean isocontour lines, is what this term here amounts to. And thus I would find that beta 2 is more likely, the true beta 2 is more likely to be 0 than beta 1, even though I found a larger regression coefficient for beta 2. So this is like putting confidence intervals on your parameter estimates. So there was one test. This first test here, I'm not doing all the math here, I'm just mentioning that these exist. So the first test wanted to know if a particular regression coefficient should be 0 or not. And the second test, this is the F test, tests if all of the members of a subset if they're simultaneously all of them 0, or the alternative hypothesis is that at least one of these coefficients is not 0. And this is true for some subset of all features. Now the test statistic this time that is true under the null hypothesis is called F. This is the residual sum of squares of this reduced subset minus the residual sum of squares of the full set divided by J. Okay, and this is distributed according to an F distribution. Here valid for a subset of J variables with n minus p minus 1 degrees of freedom. And the residual sum of squares is defined as my yi minus yi hat summed up. Okay, and if my errors are normally distributed, then both the numerator and the denominator are chi-square distributed. And if you divide these two by each other, you get something that has an F distribution. So in figuring out these distributions is what much of the early 20th century statistics has been about. Okay, so bottom line is there are tests for these two null hypotheses that either a single variable regression parameter is 0 or not, or that a subset is altogether 0 or not. Yeah.
I'm sort of missing the big picture. Like, what are we doing with these tests? What's the
Okay.
objective?
So I said that one of the motivations for doing regression in the first place is interpretation, so to find out which are the most influential or which are influential explanatory variables at all. So here you want to find out which of your features do you need in your linear regression model and which ones not. So is there unequivocal support in your training data for regression coefficient number I to be non-zero or not? Or here for an entire subset for them to be zero or not? And if I'm bringing back this example that I showed here, so let's say if we want to, I'm not saying this is the best method, but if we wanted to use least squares regression to predict if a cow has BSE or not, we have to decide which spectral channels are we going to include in our model. And these tests allow you, this t-test that I mentioned, allows you to ask for each spectral channel or for each feature separately, do we believe that it should be in the model or do we not believe it? And the f-test makes a similar statement for an arbitrary subset of variables. So these need not be, here adjacent variables in the spectrum. In an f-test, I could ask whether this variable plus that variable, if they should be included in the model or not. So fundamentally, that's an important question, because let's say you want to, this is not a linear regression, but let's say the outcome is mortality, and you want to find out if living in a particular area, close to a certain plant, or if taking a particular drug, if this has significant influence on your mortality or not. So these are binary answers, but important answers, to see is there a relation or not between your predictor and your outcome. And now these simple tests here, they only test for linear association, so this is just for linear regression, but the principle carries over.